Good morning, everyone. My name is Amal Georgi, and today I'm going to talk about our work, which is called DEISA for Dask-Enabled in Situ Analytics. This work has been done with Julien Bigot and Bruno Raffin. A binary performance gap is separating the I/O bandwidth and the CPU performance. In some fields, the traditional post-hoc processing is not feasible anymore due to limits in both storage capacity and I/O duration. In situ approaches are attractive to bypass the disk accesses and fully leverage the HPC platform as they process the data as they are generated instead of writing them to disk, then reading back them for post-processing. However, in-situ workflows are more complex to set up compared to post-up, and that's mainly due to the fact that most of the existing in-situ tools are built on the MPI programming model, which is inherited from the host simulation. In this talk, we will present our approach that minimizes those efforts by leveraging task-based programming model for in-situ processing. Concretely, our approach couples MPI simulation codes with task-based in-situ analytics using Dask through DEISA. So in this figure, we have two parts. We have a running simulation with M processes, M+1 processes in the left, and a complete Dask instance in the right. To couple the MPI simulation with Dask, we have implemented two components. The DEISA bridge in the simulation side, we have one bridge by MPI process and a DEISA metadata adapter in the analytics side. Every time the data is available in the MPI processes, it is sent through the DEISA bridges to the workers directly. Then a set of metadata is sent to the scheduler. Those metadata describe the data that we have already sent to the workers. This metadata can be then retrieved by the metadata adapter from the analytics side and used to create a task array that can be used then to submit tasks to the scheduler. With such an architecture, coupling MPI codes to Dask analytics in an in-situ fashion is easier. From the simulation side, only changing the source of the data is needed. Instead of getting the data from the power file system, the data is now retrieved from DEISA adapter. From the simulation side, an instrumentation is required to make data available for DEISA bridges. To do so, we have used PDI data interface and DEISA plugin. And of course, you can find more details on that in the paper. We have evaluated our prototype in Rich Supercomputer using a mini app, which is a 2D heat solver parallelized in MPI and an incremental principal component analysis from Dask-Enabled API. In the left side, we have all the configurations that we have tested, and you can find the results in the paper. And in the right side, we have only results for the last configurations, which is where we generate 64 gigabytes per iteration. So here we compare the DEISA results with the post-hoc results. If we consider only the MPI part that includes the simulation and the transfer for DEISA, and it includes the simulation with writing the data to disk for post-hoc, we are 3 times faster than the post-hoc version. And if we include all the iteration, including the analytics, we become more than 16 times faster than the post-hoc version. And something which is interesting here is that we are using almost the exact same coding efforts. So in this paper, we showed our work regarding leveraging task-based programming model for in-situ processing that shows an easy use as well as a significant performance gain. For the next steps, we are working on developing protection use cases, namely with the Jesila code, and we are working on supporting hybrid in-situ and transit workflows. Thank you for your attention, and if you have questions, please feel free to ask them.